and we're done. Cool? All right, let's go ahead and move on to a harder example. Now these examples, we do have shifts now. We have shifts involved. We automatically focus our attention at this h and this k value. Something to notice about these is that whenever we're dealing with this whole x minus h thing, we got to remember that we're going to take the opposite of our h value. And this is due to our zero product property. So we want the opposite of this h value. The k value we'll take as is. So let's go ahead and follow our steps for this example. We're going to list the value for a, b, h, and k. So here is our equation. Well, a is just equal to 4. B is equal to 2. H, we're going to take the opposite of this. So instead of negative 1, it's going to be a positive 1. And k is going to be negative 3. There we go. So we're done with step 1. Step 2 tells us to plot our 2 points. We have our y-intercept. It's going to be 0 and 4. And we have our second point, which is when x is 1. We multiply a and b together. We get 8. Finally, we have our h. Our shift is 1 unit to the right. And our k is 3 units down. Furthermore, we know that our horizontal asymptote, oops, let me go ahead and fix that. We know that our horizontal asymptote is actually given to us by the equation y is equal to whatever our k value is, negative 3. So a different way to think about it is that you're going to take a vertical line and shift it 3 units down. So it used to be at 0, now it's going to be at negative 3. So here is my horizontal asymptote. So this is the line we can never touch, but we can get very, very close to. So let's go ahead and plot these points and then apply our shifts. The first point is 0, 4. So we're going to say 0, 4, 1, 0, and then here's our 4. That's our first point. Okay. From there, we're going to take this point and we're going to shift it 1 unit to the right and 3 units down. So let me take a different color. I'll go red to show this shift. We're going to go 1 to the right and then 3 points down. 1, 2, 3. And this actually becomes our new point. Okay. The second point we have is 1, 8. So here is 1, and we're going to go up 8 units to 8. We're also going to apply our shift. From here, we're going to go 1 unit to the right and 3 down. 1, 2, 3. There it is. So, having these 2 points, we can go ahead and draw our curve as best as we can and bring it all the way down to our asymptote. Here we go. And there we go. It gets very close, but it never touches. And that is, we're done. So let's go ahead and move on. We have exponential growth models. So it's something that we've been looking at, our exponential growth. We've graphed them. Now let's kind of understand them a little bit deeper. So when a real life quantity increases, so this should have been an S. Let's do increases. There we go. By a fixed percent. Issue with this definition. So it should be by a fixed percent each year. So those of you guys that are my students know that this is very common. I forget to type stuff in. Fixed percent each year. Well, there we go. So when a real life quantity increases by a fixed percent each year or other time period, the amount y of the quantity after t years can be modeled by this equation. There we go. So something to keep in mind is that a is the initial amount. So this is the initial amount R is always going to be our rate in decimal, so make sure to write it in decimal. And T is our years, time, years. So this is whenever we have a real life quantity that is increased by a fixed percent. Notice fixed percent is underlined because it's not a variable, it is fixed. They're going to tell us what our percent is. So let's take an example, or let's look at an example of what an exponential growth model will look like. So here we have a word problem. Yes, word problems. It's okay. I'm going to go ahead and write the equation down. We had y is equal to a times the quantity of 1 plus our rate to the t power. So we have, in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. So we want to write an exponential growth model given the number n of incidents in t years after 1996. So instead of having y, we're going to be writing an n. So let me go ahead and erase this y, and we're going to refer to it as n for the number of incidents. So let's kind of gather some of the important numbers we're given up here. So we know that there were 2,703 computers. So our A value, or our initial amount, is 2,573. And our rate increased by 92%. So R will actually be 0.92. Remember, we keep that as a decimal. So if I want to write an exponential growth model, all I will do is plug in these values. We have 2,573 times 1 plus R. I'm sorry, we know exactly what R is. R is our decimal, 92, and T is the number of years. If we kind of elaborate on that, I have the work done on the side. This actually gives us that n is equal to 2,573 times 1.92 t. All right. This is what our model will look like. So if it says to figure out the number of incidents t years after 1997, about how many incidents were there in 2003, that is actually a 7-year difference. So we're going to plug in that time is going to equal 7 years. So all we have to do is substitute that in. You would definitely use calculators for this. We can use our iPads. Those come in with built calculators now, and we can work this out. So by solving this, we end up that our n, so the number of incidents, is actually increased to, or in this case decreased, to 2,400, increased to 247,485 viruses after 7 years. So that is a big increase. There we go. Cool. So we can use the graphing calculator to also model this and make predictions. So we'll see that in class. The last interest model the last model that we're going to look at is the compound interest model. There you go. All right. So consider an initial principal, P, deposited into an account that pays an interest at annual rate R, expressed in decimals again, compounded n times per year. The amount A in the account after t years is given by this equation. So what does this mean? This means if you have a bank account and you invest it, or you actually put, like, let's say a savings account, you put an initial amount of money, that is known as your principal. That is the principal amount. Now, usually savings accounts come at a certain rate. So this is your rate. And they get compounded, in this model, the interest, they get compounded n number of times per year. So this is the compounded times, and t is going to be a year, or the years. So how many times do they get compounded? We're going to be using this model to also model real life situations, pretty much. So let's go ahead and take an example, look at an example of what this means. Example 6, we have you deposit $4,000 into an account that pays 2.92% annually. Find the balance after 1 year if the interest is compounded with a given frequency. So we're going to write down our initial formula. We have that not y, but a. We have that a is equal to our initial principal. Our initial principal, 1 plus the rate, number of times compounded, times number of times compounded times time. So we're going to go ahead and plug in these values. P is our principal, that's 4,000. We have that our rate is equal to 0.0292. And A tells us quarterly to figure out how much this thing is compounded quarterly. So how many quarters are in a year? Well, 4 quarters are in 1 year. And T is going to be 1 year. So if we plug all of this in to solve, we have 4,000, 1 plus the rate, 0.92. We forgot a 2. Over 4. And we're going to have to the 4th power. If we use a calculator and solve this, we get to very neat numbers. For A, we actually we conclude that it gives us $4,118.09. So after a year, we're actually going to gain $118 profit for just keeping the money invested in a savings account. Now let's do an example where it's done daily. So daily, the only thing that's changing now is going to be T. T is going to be, N. N is going to be 365 for 365 days a year. So again, we're going to plug in to our formula. We have that A is going to be 4,000. We have 1. Our rate stays exactly the same. The only thing that changes, 365 and 365. When we work that out, we end up with an approximate number of 4,118 and 52 cents. So it makes sense, since we're getting compounded over the time span of 1 year, we'll pretty much approximate the same thing. We're just up by a few more cents. Alright guys, that's the entire lesson. I hope this helped. It was a bit lengthy, about 27 minutes video. Again, please feel free to forward and pause at any moment and revisit only the parts that you deem necessary. See you guys.